they're very related in mathematical parallel to these things. And what we'll go through is kind of a little bit of the fundamental factor, but then show the linear system technically is simple in the calculus controllability and observability. The question is, what is it? The idea of controllability is a system's control. It can go from any initial state to any later state in time. We've defined it in finite time. Right? So I can set any x given some initial state and some control. And I can make every single state go through some values. Observability is parallel to it. And basically, it's observable if every state can be determined from the output. This is controllability. Observability is that every state some x every time can be determined from the output. So looking at this whatever output is like, I can figure out what every single state is. Some things are very obvious about controllability and observability, others not quite so obvious. Let's look at kind of an obvious one first. One example. Here's our state equation. Put it in diagonal form, so it's very simple. So it's set to actually write out every single state equation. So x1 dot is minus x1 plus u, x2 dot minus 2x2 plus u, x3 dot minus 3x3. Okay. All right, so it's actually, draw that out, let's block diagram. Over here, we'll do a nice block diagram. Here's u, or input, and y is the output. So a representation of those state equations, really, it's how do we get from like an x1 dot to an x1 by integrating. I can draw these things each integration. So to start off, here's x1 dot. If I integrate, put it in the plus, show integration. There's x1. Right? Just integrate x1 dot to get x1. Well, what is x1 dot equal to? Well, it's equal to minus x1 plus u. Okay? That's essentially the first state equation. The second one, do the same thing. Integrator is x2, and let's write x2 up here. Again, x2 dot is equal to minus 2 times x2 plus u. And then I can do it for x3. Mess up the room, but we can just close it in. And it's equal to 3 minus. Okay. All right, then the outputs are sum see how we got those? Now, the question is, can I control all the states? So is there some U that connects to all those states? So U obviously connects to x1, so I can control x1 somehow. It connects to x2, so I can control x2 somehow. So there's no pathway to get to x3. There's no U that I can go somewhere here to affect x3. Right? So this system is, x3 is not controllable. Okay, does that make sense to everybody? Yeah.
Would we consider x3 controllable if it were a function of x2?
Could be. I'll show you an example of that. Yeah. Okay. Is it observable? Do all of these states affect y? X1 obviously does. X3 obviously does. What about x2? Is there any pathway from x2 to y? No. No. X2 is not observable. Now, answer your question, can we, another system that would be controlled? For instance, what if x2 also went into x3? Is x3 now controlled? Now, there is a pathway from U through x2 to x3. Presumably, I can figure out some U of t that will affect and control what the value of x3 is. Okay, does that make sense? Well, even though I have this pathway here, x3 may still not be controllable today. I can have conflicting things and cancel it out. We'll get to those. Now, is x2 observable?
Yes.
Yeah. We've now passed x2 through x3. Yeah. So now they're both controllable and observable. Right? Can I get the idea of what controllability and observability is? Give you an example of a controllable but not observable system. One we've been working with functional electrical stimulation of muscles, nerves, and control muscles. All your muscles, all they do is pull. Right? So you have antagonist muscles to control your joint directions. So I can see where the output torque or output position of the muscles are, of the joint. Right? And I can control, stimulate each muscle. Okay? But can I observe the opposite of each muscle individually? No. No, I don't know what each force is in the muscle. All I know is the difference in the forces. And I don't know the total sum of them. That kind of makes sense. So you can control your limbs, you can tighten up all the muscles, haven't changed my output. So that's a system that's not observable, but it is controllable. How do I then make a proper controller to make sure that even though I can't observe it, I can make sure my muscle forces don't go too high or within the right ranges? Any ideas on that?
Could you like check electrical input?
Well, we're actually stimulating with electrical. One is the idea is we look at EEGs.
Okay.
On that. Yeah. And if you're simulating the motor neurons, you can do that. Yeah. So anyway, that's just an interesting part we have. It's a non-observable system is controllable, but your eye actually can observe everything. You have sensors, force sensors in each muscle. Right? So, basic idea here. Get into a little bit of the nitty-gritty. This is for a nice simple system. these change matrices. We did introduce what we call the controllability matrix and the observability matrix. We use those to what? We use transform our A matrices into what we call controllable form or observable form. Kind of see why we call those things here. The question is, what do we mean by these terms? I can explain these before. Very formal definition here. You notice this is for time varying systems. We're going to go very general here. Most of what we do in this class is time invariant, which means A, B, C, D matrix are not functions of time, but they could be functions of time. In fact, in real life, they are functions of time. Things vary. We'll look at it very generally here. The basic idea for some state equations, they have to be linear to time varying. As control of any initial state, there exists some continuous input signal such that the corresponding solution I can drive it to the origin. That's a formal definition. Basically means I can drive it to some known value. Right? That's controllability. So there's a theorem here. And this is in a, Ken kind of does this in some form. A lot of books go through this, go through kind of the theorem and then show how simple it gets for a nice linear time invariant system. So systems control if and only if this n by n matrix is invertible. This is W matrix. Right? You got to figure out what this W matrix is. B is a state transition matrix. B is B matrix for a system. Right? And W is noticed as controllability gramming. Great mathematical terms here. Controllability gramming must be positive definite for controllability. Right? General can function of time. Right? And can really be a messy thing to find. So it's usually if you really need to solve this thing for a time variant system, you need to do it numerically. But we'll look at the sufficient conditions to check for this. So what we'll do is let B matrix be some constant for this, it's K naught, and put K in this form of the A matrix, time varying A matrix, times KT and so forth. So it's a series form for this K matrix, or K. And then you can find that state transition matrix type B has to form in the state transition matrix times all these Ks. Right? We'll go through all the great detail to prove that, but it's a provable thing. And for any positive integer, J means I'm taking the J plus 1 derivative of this. I have to change I have to do a variable substitution for sigma to do this derivative. I can show that, okay, state transition matrix type B is going to be derivative of state transition matrix times K, right? Or simply comes down to a. So that one includes, I guess, term there, got out of order, sorry. Reason being is sigma times A times K plus derivative all simplifies to state transition matrix times this matrix K. So, okay, T is going to be simply the derivative of state transition matrix times B. Okay. A lot of proof to make this something fairly simple. So the sufficient theorem is where B is, say, Q times continuously differentiable, and A of T is Q to the minus 1 times differentiable. All I have to do is check the range, and this thing must be full range. A range must be full range. Now, for the time invariant, the case is just B, A times B, A times A times B, and so forth. All right? It gets to be very, very simple. All right, so from a very general form to a very simple form. So, proof of this is that rank condition fails if and only if the controllability gramming is not invariant. All right, so what's it mean by invariant? Here's a programming again with the state transition matrix put in, E to the AT. You guys have been working on this last homework. There exists a non-zero vector X such that X transpose A, B must be equal to 0 for all K's. X times the controllability gradient W, substitute in that into the interval. So if W is not convertible, there exists a non-zero X, right? Or X, W, X must be 0. X state transition matrix B must be 0 for all time within that range. It must be 0 at initial time, differentiated so many times. I'll do this quickly. Basically, you've got for a linear system, X transpose A, B, the same controllability matrix here, must be 0. Okay? So since it's a proof of this thing, all we need to do is make sure this guy is full rank. It's the easy part. Observability, same type of idea. It says that for the state equation is observable if in their time frame some initial state is uniquely determined by corresponding response. So basically it's saying that our states affect the output. If the state doesn't affect the output, then it's not, or some combination of states don't affect the output, then it's not observable. Very similar proof to controllability, do the same thing, except now state transition matrix uses C matrix, and B comes from the whole nest. Let's see what you think. Same form. Go through all that. So for a time invariant, it says that the rank of C, C times A times A, whatever, must be full rank. That's the case if it's observable. Right? Yeah.
Sorry, I think I'm just missing something. I'm not sure what it means to be full rank.
What does it mean, full rank? Yeah.
Each row or column.
What's the easy way to find it? Determine. In fact, find rank. Let's show that. So let's do some examples of